Okay, welcome everyone to our next guest lecture in Grid Interactive Buildings. And we have a pleasure to have Dr. Kazmi here with us. He is currently an assistant professor at KU Leuven. He focuses on data science and decision support tools for the energy transition. He has a PhD in electrical engineering from KU Leuven, MS degrees in sustainable energy technology from TU Eindhoven and Politecnico di Torino, and a B in electrical engineering from the National University of Sciences and Technology in Pakistan. He contributed to over 50 peer-reviewed publications and played key roles in several clean energy startups. And in 2021, he won the International Institute of Forecasters Annual Award for his research on value-oriented forecasting. So who better to talk to us about forecasting energy use today? Hussain, please take it away.
All right. Thanks, Zoltan, for having me and the introduction. I hope you can hear me all right.
We can hear you perfectly.
Okay, great. Right. So thanks everyone for joining. Good morning, good afternoon, good evening, depending on where you are. This is going to be about energy forecasting, but it's also going to be a bit of a high-level introduction because Zoltan mentioned that many of the students in the class are construction and building engineers who don't necessarily have a big exposure to how the electricity system works. So we will take it slow, and if you have any questions, feel free to send them in the chat or also raise your hand and we can answer them during the talk, after the talk. Either way is fine for me. Right. So here is a getting started slide. So this is a picture of KU Leuven, of the many different campuses that we have in the city. So we are around 10-20 kilometers from Brussels, not too far away. And the campus on the top left-hand side is basically where we work. So we work very close to that. We work in the stables next door to the castle. But yeah, that's basically our view when we walk out of the building. Right. So here is a bird's eye view of the PowerPoint that we are going to see in the coming hour. I'll briefly talk about how the electricity system is organized. So this should hopefully not be too mind-blowing, but we will try to go over the basics. I will talk about some of the recent trends in demand and generation as they're arising at the moment, specifically in Europe and even more so for Belgium. But many of the trends also hold for other parts of the planet, so they should also be similar in the US as well. Then I'll talk briefly about some of the use cases and challenges that are emerging in this new power system, especially related to the forecasting techniques that are applied historically, and that will need to be developed in the future. And then finally, we will conclude with a few slides on how to develop forecasting algorithms, some key considerations that you need to keep in mind, and then we can build a discussion from there in an interactive manner. Right, so let's get started with the electrical system. So electrical engineers like to say that the power grid is the most complex engineering structure that humanity has ever created. A bit of hubris, but also like some reality to that claim, because the power system is very complex in the sense that unlike other commodities, electricity has to be completely balanced at all times. So the demand must be equal to supply. Otherwise, bad things happen on the grid, as we will see in a minute, that they are happening now, increasingly so. And things will get even worse in the coming years. So this is how the classical electrical grid looks like. Not really. This is a 2D depiction of the overall grid. So what you see at the very left-hand side is a generator. This can be a nuclear power plant. This can be a coal power plant. Increasingly, we see these are renewable energy systems. So a lot of big, giant wind farms, but also lots and lots of solar PV being added to the system as well. This gets connected to the transmission grid, which basically is usually on a very high voltage level. So this is going to take the generation from those big power plants all the way to the distribution network in cities and other big population centers. So you are going to get the electricity down to cities in this way. And then inside the cities, you use basically the distribution network to provide the electricity to the end users, who are here referred to as retail consumers. These could be households, these could be commercial buildings, for instance. These could also be industrial users. So, for example, large-scale factories, giga plants for producing batteries, aluminum smelters, all of those kind of things. So they are at the very right-hand side of this picture. Historically, in this picture, there was a very clear direction of power flow. So you would have electricity that would be generated on the generators. That's literally their job. And it would be consumed by the retail sector or consumers, which is literally their job in this picture as well. And the electrical grid would be there to support the flow of electricity from the generators to the consumers or the retail side. That held true for many decades until we started seeing new things over the last few decades, which see that we also have power flows in the reverse direction. So going from the retail side towards the distribution networks, but then even more so on the transmission side as well. So this is changing the shape of the electrical grid already in unexpected ways. And there are quite a lot of drivers behind this sudden and rather drastic shift in the operation of the electrical grid. Let's take a look at some of those big drivers. The first one is, of course, that the retail sector has gotten a lot more efficient at consuming electricity over the past few decades. This is because electricity or energy costs have risen considerably over the past few decades, but also that we have become more and more aware of the negative effects that burning a lot of fossil fuels has on the climate. So we have seen a lot of improvements in energy efficiency on the retail side. This means that the demand has gotten lower to achieve the same end goals. At the same time, we have also seen an increasing electrification of industry and residential and commercial sector. So this has led to the opposite effect in the sense that it has led to an increase in the demand of electricity, while it has also lowered the demand for energy in other sectors. So a very good example of this is the electric vehicles, which are increasingly displacing fossil vehicles or ICE cars. And there you can think about the fact that previously you would have to go to the pump to get your car fueled, but now you just use the electrical sockets in your household. Unfortunately, that also has other implications. So for many European households, this basically means that if you have an electric vehicle, then you are essentially going to double the amount of energy that you consume over the course of a year. So I should reformulate that as double the amount of electricity that you're going to consume over the course of a year. So that's the second effect that has happened in the last few years. And the final one, and perhaps the most important one, is the proliferation or the rapid proliferation of solar PV systems on the rooftops in these households. So not only have we gotten a lot of solar PV systems in people's houses, but increasingly what we are seeing is that they also come coupled together with either simple electric batteries or electric vehicles that also provide some kind of vehicle to grid or vehicle to home technologies as well. So increasingly, again, we see that the power flow has reversed from the generators to the consumers to electricity being generated in the retail sector and then flowing in the reverse direction. Now, what does this mean practically on the distribution sector? So for the distribution grid, you can think about that as the wires that connect the feeders and the transformers to your households or to other big buildings in the neighborhood. This has meant that there is a lot more issues that are coming up for the distribution grid as a whole. Two main problems that emerge always are voltage related and congestion related. And these both are quite simply to be understood as there is either too much electricity being consumed in the grid, in the distribution grid. That would be perhaps the increase in electricity demand due to heat pumps in winter, where everyone in the neighborhood is going to consume electricity when previously they were using either the gas grid or burning wood or something else to heat up their homes. At the same time, this can also be in the opposite direction, that during the summer months, when electricity demand can be rather low in places where there is not a lot of air conditioning needed, unlike Texas, I guess, but in Belgium, where we don't have a lot of air conditioning during the summer, you would have a lot of solar production, but not a lot of demand, which would mean that the electricity would actually flow in the reverse direction, leading to overvoltage incidents on the grids. And this is quite unprecedented because there is no real historical precedent where this would be an issue. So this requires grid operators, distribution system operators to think about how to solve these problems in a creative manner. Historically, what they have done is what's known as grid reinforcement, that they would put thicker copper cables to fix these problems. Basically, that's a very simple solution for which no one ever got fired, that you simply increase the amount of infrastructure that you have, kind of similar to building new roads to solve congestion issues. But if you talk to urban planners, you will invariably hear that that never solves the congestion issue. In electrical systems, that may solve your congestion issues, but it comes at a huge cost. And increasingly, what we have seen is that grid operators are leaning towards more active network management, more active demand management, and we will talk about that briefly in a few slides. This also has implications for the transmission system, and this you can think about the infrastructure that needs to be built, for example, to take the electricity that's being generated by those huge offshore wind farms and supply them to the big cities, well, coastal cities often, but anyway, like the big cities or population centers that are going to consume that electricity. So this has led to the emergence of what's known as the duck curve, which is now quite infamous. This was initially popularized in California, and now it is visible in many different countries and regions of the world. So the idea is simple, that during the afternoon, you have a lot of solar on the system, and that really takes away from the net demand. So basically, you don't really have a lot of demand during the afternoon, but during the mornings and during the late evenings, when there is not so much solar production on the system anymore, you have high demand. And that basically means that power generators need to come online in the morning, then go offline during the afternoon, and then come online again during the evening, and then go offline for the evening or night as well, which basically increases their costs, but also increases wear and tear, but also means that we need to have this high ramping capacities available on the system on the one hand, but also that the capacity needs to be there because the solar generation is not going to be there 24/7. This also means that generators need to adapt their behavior, because for many years, the mantra was quite simple, that if the demand is there, we will be able to provide it and earn revenues for that. Unfortunately, that's no longer the case, because the supply system is increasingly transitioning from fuel-based systems to weather-based systems. That simply means that you can no longer control how much electricity is going to be generated on the system in the next 24 hours or in the next week even. You can predict that using forecasting techniques, but you can still not directly control it, because even if you know that it's not going to be sunny, that doesn't really help you fix the capacity problem of finding that generation. So you still need to have the backup plans for days when it's not going to be sunny or when it's not going to be windy, etc., etc. All right, so that's the end of the whirlwind tour of the electrical system. Quite simple stuff, but if anyone has any questions, feel free to jump in and ask. Otherwise, we'll start talking about some of the recent trends in demand and generation.
We can move on. Thank you. It's good.
Okay, great. Then this is basically going to build further with some numbers on the things that we have seen in the previous section. This is how electricity demand is foreseen to be in the next 10 years. So you see that in 2022, we are at 100%. And then this is how it is hopefully or possibly going to evolve in the next 10 years. So what you see is that for most European countries, we will have quite substantial increases in the amount of electricity that we consume. This is mirroring in many ways low-income countries where there is high rates of electrification still ongoing, and then the demand rises quite considerably year on year. But these are already countries which are industrialized and everyone has electricity access. Even so, because of many different factors, we see that, for instance, in Denmark, the electricity consumption is expected to double almost compared to where we are today. In Belgium, it's also expected to rise by more than 50%. And we can look at the individual drivers in a bit more detail in this case. So this is a picture from the Belgian transmission system operator. I hope you can see my cursor. But the vertical line here is where we are today. And on the right-hand side, what you see are projections from the grid operator about where we are headed towards. So you can see that over the last 15, 20, 25 years, the demand has actually stayed rather flat, or it has even gone down by a bit. This was especially true during the COVID years. But it has really fluctuated between 80 and 90 terawatt hours, which is reasonable for a country of Belgian size, around 10, 11 million people. But in the next 10 to 12 years, what we expect to see is more than a 50% increase in the amount of electricity that will be consumed in the borders. And then you can see like where it's really coming from. So one of the biggest increases is actually from heat pumps and electric vehicles. So that directly affects people who are planning and designing buildings, because previously we didn't really have this huge amount of electricity demand on the building or household level that is going to be there in the next few years. The remainder actually comes from industry, so I guess that's not so relevant here, but there again, it's quite a lot of buildings related stuff. Like, for example, a huge draw is from data centers, and cooling or the computing requirements for the data centers is also very much related to infrastructure that is then planned and optimized by building engineers as well. So there are unexpected links here and there in this whole picture. And at the end, many of them tie back to the built environment as well. So, like I said, related to people in this webinar, I guess, there are three key factors that are going to increase or lead to this increase in Belgium. This is mirrored mostly in many European countries, but I guess also to some extent in the US as well. So the first factor, and that's really big, is that there is a projected ban on the sale of internal combustion engine cars by the end of the decade. That's not really that far away. That also means that by 2035, we expect more than half the electric vehicles, more than half of the cars to be electric vehicles, going from 5% last year. So that's like an increase of more than 10 times in around 10 years. And that's a huge problem for the electricity grid. At the same time, we also see that there is going to be a ban on connecting new buildings to natural gas infrastructure. This is because of many different factors, but what this essentially boils down to is that in the coming years, we will see most of the houses stopping with heating from gas or oil-based boilers and replacing that with electrical systems. So that's going to, again, lead to quite a lot of changes on the built environment side. Finally, we also expect there to be more and more requirements on reporting of the EPC labels. So the EPC label is basically the energy performance certificate. So you get like a label from A to something like G, where the lower it is, the worse your building is going to consume electricity, or the more it's going to consume electricity. So that's another thing that will become mandatory, or has already become mandatory, to report that for buildings, which is hopefully going to spur investments in energy efficiency as well. So that's the demand side. Let's look at the supply side briefly, and then we'll talk more about forecasting in a minute. So this is what is being projected for the coming decades in global scale, where we see that fossil fuels are expected to be phased out in the coming decades. But what is even more remarkable is where we are headed towards with the wind and solar generation. So we are going from less than 10% at the moment, or around 10%, to something which is going to be more than 50% in less than 2 decades. So that's a huge change, which is going to take us from a power system which is primarily driven by fossil fuels and is rather predictable to something that's very much driven by weather and is not necessarily predictable and even less controllable. So huge changes, huge challenges coming up for all of us, I imagine. So zooming in, here is what is expected to happen on the Belgian scale, which is arguably not going to contribute in a meaningful way to the generation on a global scale. But that's how it looks like in the coming years, the projections. So you may notice that there is this big black curve that has largely disappeared in the last few years, and that was coal. So we do not consume any coal to generate electricity, but we do consume quite a lot of natural gas and quite a bit of nuclear, which is being phased out at the moment. So there is also quite a bit of gas, but what's perhaps the most remarkable is that we will have quite a lot of wind and PV systems integrated into the generation side in the coming years. You may also notice that here the generation is less than 100 terawatt hours, so that's the unit on the y-axis. But if you look at the demand side, that's actually going to 130 terawatt hours, or even more than that. So there is quite a big discrepancy there between the planned demand and the planned generation. And that is, again, further cause for concern for the coming years. Because not only does this mean that we won't have enough electricity to meet the demand, it also means that perhaps we may fall back to consuming fossil fuels to power that electricity need, or stop with the electrification process altogether, which fundamentally means that we will be reneging on the climate pledges that countries have made. So this is true not just for Belgium, but for many countries in Europe, in fact. The Belgian electricity grid is very well integrated with the European electricity grid. So this is kind of similar to the US, where the power grid is, again, well connected in certain regions. So Texas is like a small island of its own, I guess. But then there are several other regions that are quite well connected and integrated with each other. That's also the same for Europe, where there are many bottlenecks that exist between different countries, but then there is a lot of investment that's going into interconnectors at the moment. What's actually more interesting to notice is that things change very rapidly from one year to the next year. So on the left-hand side, you see a picture of what was happening in 2021, where France was actually the biggest net exporter in the whole continent. And then we go to 2022, when basically a lot of nuclear power plants went offline for planned maintenance, and that lasted a bit longer than it was planned, which eventually meant that France became a big net importer of electricity. So this is again like a benefit of having an interconnected system, that if you have a shortfall of electricity generation, you can hopefully rely on your neighbors to provide you with that electricity. But in many cases, that can also lead to other problems because, for instance, the neighbor that you were counting on to provide electricity has planned or unplanned outages in generation potential that are going to lead to problems with your security of supply. So people might have no electricity to consume at some points of the year. So just a thing to keep in mind when we talk about electricity demand as well. Okay, that leads me to opportunities and challenges for forecasting, and then we will start to also head towards the building and urban scale. That's perhaps a bit more relevant for the audience. But in the meantime, I see that there is a question in the chat from James, which we can take before moving on. Okay.
Yeah, go ahead. You can take that question.
Yep. So why don't the distribution utilities put batteries at the substations so they can smooth the variation in rooftop solar? So yeah, that's a good question. I guess that's $1 million question, especially in Europe. So there are several reasons for this. In some places, this has been trialed as pilot projects, but for instance, in a large Horizon Europe project, so like a large Europe-wide project that we were working in a few years ago, together with some Dutch distribution system operators, we actually had this idea that we would have residential batteries, so people with their own batteries in their households, and a distribution scale battery. So that would be placed next to the substation, I guess. That would be able to provide voltage support and basically smooth out the variations in rooftop solar, but also mean that the over voltages and under voltages might be solved a bit. That is often blocked by legislation because the distribution system operator is often a regulated entity that cannot participate in electricity markets to make profit. So that essentially rules out a lot of the use cases that the distribution system operators might be interested in because legislation has not yet caught up with the actual problems that we are facing on the electrical grid. Long story short, basically that means that in many cases, while these solutions would be able to solve the problems on a technical perspective, they cannot do so because of a regulatory perspective. But yeah, that is indeed a great technical solution that might work in many situations. Yeah. Okay, then continuing, this is basically forecasting. So in this section, we will talk about some of the opportunities that exist, some of the use cases that people are using forecasting algorithms for. And then we will talk about many challenges that have emerged in the past few years, and where you can contribute is going to be in the next section, I guess. All right, so we have already seen some of these pictures. This is an example of a forecast that grid operators are using for planning purposes. So this is true for the transmission system operator. This is one, for instance, that the transmission operator of Belgium has made. But the same forecasts are also made by distribution system operators because they also have to see how the households in their neighborhood are going to consume more electricity because of heating, because of electric vehicles, because of other possible changes in the demand side, but also because of the renewables that might get installed on the rooftops or in the facades of buildings. So this is one example of long-term forecasting where you predict for several years into the future for planning-related purposes. One thing that I always recommend is to take a look at the long-term forecasts that agencies such as International Energy Agency, the IEA, have made about the proliferation of renewables. So if you look at the long-term projections for solar proliferation for the last 20 years, you always see that they are extremely pessimistic and super biased towards the lower side. So that's something that is also the case with long-term forecasts. That is always a bit tricky because these are not necessarily data-driven forecasts. They are actually built using scenarios. A different, completely different use case is short-term forecasting, which is basically trying to figure out how much electricity demand or generation there is going to be in the system, in a building, for a specific appliance, over the next day, over the next hour, or even over the next week. And then you can really use this information to optimize the energy flows. But you can also use this to do risk-constrained planning. So for example, you can say that if the demand is actually going to be much higher than generation, then you need to incentivize the demand to be lower, for instance, or you need to contract additional generation, or you need to find storage in the system. So you have a few levers to press there, but having this information really provides you with the ability to fix those problems in a proactive manner rather than a reactive manner. So you basically see here, these are grid forecasts on the demand side that are created by the Belgian transmission system operator. So this is openly available. So for most of the European transmission system operators, they have to create these forecasts for the next 24 hours at least, and then they have to make those forecasts publicly available. So you can go to ENSO-E transparency platform and find all of these forecasts for yourself, which we did a few years ago, and then we analyzed their quality, and we will talk about that in a minute. But what you see here is basically 10 gigawatts of electricity demand, which is roughly the peak demand in summer in Belgium. But you also see like several other things here. So you see the measured and upscaled, which is in orange, but you should also see the green curve, which is the most recent forecast, the gray curve, which is the day ahead forecast, and the light gray curve, which is the week ahead forecast. So all of these are essentially talking about the different time horizons at which this forecast was made. So for instance, if you look here on the 6th of July, in the evening, you will see that a week ahead, the grid operator thought that there would be demand for more than 10.5 gigawatts, but in reality, it was slightly less than 10 gigawatts. So what is actually nice to see here is that as the time horizon gets closer and closer to the point of delivery, the forecast accuracy and quality actually improves. If the opposite was true, then you would know that something has gone very wrong. So yeah, sometimes happens. And that's why monitoring your forecasts is also very, very, very important. On the right-hand side, you see a zoomed picture of around the same period in the year. So that's basically this day. But there you also see some dashed lines. And what those dashed lines mean in this case is the quantile forecast for the same period. So basically what happens quite a lot in the power systems industry and not enough in the building sector is the use of uncertainty-aware forecasting. So rather than predicting just what is going to happen tomorrow, we actually predict a range on what is going to possibly happen tomorrow. Because if you think about what's going to happen tomorrow as the demand in a particular building, you cannot necessarily say that the demand is going to be 3 kilowatts. It might be 3 kilowatts, it might be 3.1 kilowatts, but it might be 2 kilowatts or something else. So you want to make the most accurate forecast possible, but you also want to provide some uncertainty estimate, some prediction interval on how uncertain you are about your predictions. So that's something that happens quite a lot in the power systems and in many other industries as well. In building sector, that's happening more and more, but yeah, it doesn't happen to the same level just yet. So here what you see are the P10 and P90 intervals. And the idea is that 80% of the time your observations would lie within these intervals that you have predicted as the prediction intervals. And up to 20% of the time, the actual observations would be outside of your prediction interval. So in this sense, you can plan accordingly. So you can make these prediction intervals like P1 and P99. And then you know that only 2% of the time the observations would lie outside of these prediction intervals. So quite useful when you're planning with these forecasts, but at the same time, not necessarily always done, and quite computationally complex as well. Okay, so far we have focused on the very right-hand side of this picture, which is the country level. But at the same time, we also have a lot of the other sectors that are interesting as well, perhaps even more so for you people, with the building side, with the district side. You can even consider the same for device level forecasting as well, that you may want to forecast how much electricity demand your heat pump has, or how much electricity demand your electric vehicle has. You can consider the electricity demand at a household level or at a big commercial building level, but you can also go to the district level where you say that what's the electricity demand for the entire city of Austin, perhaps, or of Leuven, or of some other city that you're interested in. This in itself leads to some challenges. So this is a picture from an analysis that we did a few months ago. But this is quite well known that if you have like a single household, the electricity demand of that household is going to be extremely chaotic, noisy, rather unpredictable, because there is a lot of human stochasticity to that. So this is a single household, so you can think of yourself as around here. If you aggregate 1,000 buildings, and this is for a data set from London, then you basically end up getting this very nice and smooth time series, which essentially is rather easy to predict and not too much unexpected things happen. So you kind of know what's going to happen at a district scale, which roughly is the same as 1,000 buildings. And then you can see how it goes from one end to the other extreme. If you go all the way to national level, then it gets even more regular. So basically, you go from like having possible errors of more than 100% to less than a couple of percent at a country scale. So having said all of that, where are these forecasts for electricity demand used? So for instance, let's consider this picture, the first one. So if you have this electricity demand at a household level, in many European countries, what you can do is you can take this electricity demand, and instead of paying the retail rate or a fixed rate or a fixed tariff for electricity demand, you can actually go to the day-ahead electricity prices and essentially consume more electricity when the prices are low and try to consume less electricity when the prices are high. So that's generally the idea that you can now even follow as a simple household, but that's also the principle that electric utilities and other parties in the electrical system follow in liberalized markets. So that requires a brief explanation of how the electricity market works. This is going to be an even more whirlwind tour than the discussion on the electrical system. So I will just focus on a couple of the elements here, and then if there are any questions about that, we can discuss them or take them offline. But there are several different electricity markets that exist. There are some physical products, there are some financial markets, but the most important one arguably is, well, the first two on the top row here. So they are the most actively traded ones. So you have the futures and forwards market, where basically utilities buy most of their baseload electricity demand. Then on top of that, there is the day-ahead market. So this is basically something that you are going to decide at 10 o'clock today, how much electricity demand there is going to be tomorrow in your portfolio of buildings, for instance. Or if you're a household, you're going to say that tomorrow at 3 p.m. I will consume electricity to charge my electric vehicle, stuff like that. The day-ahead market is on an hourly time resolution, but then you always have misforecasts. So you make incorrect forecasts or predictions about the next day, which means that you're then going to have to somehow correct those errors, and that typically happens on the intraday market where people fix their incorrect forecasts. And then if there are finally any remaining forecast errors, so you said that you will consume 100 megawatts, but in reality you are consuming 110 megawatts, then you're going to be hit by an imbalance penalty, and that happens really on a sub-hourly level. So this is quite a fast market. So if you're a building portfolio manager, you can think about all of these as potential opportunities to create extra revenue for your building. Because for instance, the day-ahead market has some arbitrage potential in the sense that it's a bimodal distribution. So during the afternoons and during the evenings, the prices are typically higher. So if you can somehow consume electricity not during those hours, for example, for heating the building or for example, for charging the electric vehicles, then you can save quite a lot of money. And that can be through algorithms like reinforcement learning, but you can also use simple model predictive control or even rule-based controllers as well. But to activate all of those, you need forecasts for how the electricity market is going to work on the one hand, but also you need to forecast the actual electricity demand or the baseline electricity demand that you would have for a certain given price vector as well. I will skip this in the interest of time, but we can come back to it if there is interest in it. So I just want to say that I did mention that electricity markets are something where you can perform arbitrage, but this is not without its risks. So this is the day-ahead electricity prices for Belgium over the last few years. Historically, these prices have oscillated between 30 euros per megawatt hour to around 50 euros per megawatt hour, with some extreme cases as well, but not too many. Something that happened in the last couple of years, which was very unprecedented, was that electricity price averages went up by almost a factor of 10. So we had 250 euro per megawatt hour prices on average, but even more than 3,000 euros per megawatt hours prices quite regularly that we're seeing, which is completely unprecedented, and it's completely unaffordable for residential users as well. I guess people in Texas also saw something similar in the big storms a couple of years ago, if I correctly remember, when electricity prices went to $10,000 per megawatt hour or something in that range. So quite comparable. The only difference that in Texas it happened only over the course of that storm, and I guess somewhat in the aftermath of that storm, while in Belgium and in much of Europe, this situation lasted for a long period during the year of 2022, which led to a huge increase in energy poverty, but also unprecedented increases in the profitability of energy companies. So if you could forecast these situations correctly, you could make a lot of money at the end. Okay. So this means that there is a lot of need for demand response with the variability on the electricity prices. And that is going to come through several different sources. So the industrial demand response is going to be an important contributor, but we will also get more and more flexibility, like demand flexibility or demand response potential from electricity sources like EVs, so electric vehicles, and also heat pumps. So basically, in this picture, what you can see is that if Belgium does not activate enough flexibility from electric vehicles and heat pumps, it will need to have at least 1,000 megawatts in additional generation. 1,000 megawatts, I don't know if that means anything to the audience, but that is roughly the size of a nuclear power plant. So in the next decade or so, if we cannot activate the flexibility from electric vehicles and heat pumps, then we will need to build an additional nuclear power plant just in Belgium. And you can, well, basically extrapolate this to a European scale or also to an American scale, and then see how much cost savings there exist with these opportunities. All right. So before talking more about forecasts, I guess that we have a couple of questions. I don't know, Zoltan, how strict you are with wrapping up in 15 minutes? Because
I have to dismiss class in 15 minutes. You can keep talking as people want to stay on. Some people may leave, that's all. It's up to you at that point.
Okay. Yep,
you can take the questions.
Okay, then let's take the couple of questions and then try to wrap up quickly. So what are the benefits of aggregating multiple building energy consumers? Also, I think that we can do cloud-based aggregation to implement it technically, but is there an advantage if you use the cloud? Okay, so good questions. So what are the benefits of aggregating multiple building energy consumers? So the most obvious answer is that many flexibility products only exist if you can aggregate enough flexibility. So for instance, if you want to participate in frequency regulation markets, that basically is to deal with the imbalances between the demand and supply, then in many European countries, you need to have at least 1 megawatt of flexibility available. Now, that's very unlikely to come from a single building, even if it is a very large commercial building. So you will invariably need many different buildings to activate the necessary amount of flexibility on the frequency markets. This also essentially holds for the day-ahead markets and the other types of arbitrage that you can do in the electricity markets. Because if you have only a single building, you don't really have any benefit to get by participating in the day-ahead market, because the risks are huge that you may suddenly have 100 times more expensive electricity. But the upside is rather down, because perhaps you may save like 20% of electricity costs on average. So you are exposing yourself to a lot of risk for not a lot of reward. So in that sense, it's also, again, much nicer if you can spread this risk out over a lot of different consumers, because then you don't really have the individual risk in that sense. The second part of the question about the cloud-based aggregation. So yeah, that's then relating to the idea of virtual power plants, I guess. So yeah, that's essentially how this is being done. So there are many advantages to doing it that way, but I guess also many disadvantages to doing it that way, like privacy, data collection and aggregation. But I guess we don't really have time to talk about those in too much detail for now. But that's essentially how these programs are being implemented in most cases. All right, so did I hear about real life use cases of reinforcement learning implementation, or are they mainly MPC? So in many cases, it's neither. It's often just rule-based control. That's unfortunately, depressingly, still the reality. Increasingly, you see MPC systems coming online. In terms of reinforcement learning, there are a few pilots that we have seen. But to be honest, the complexity with those reinforcement learning systems are such that you cannot necessarily implement them directly out of the box. So yeah, I wouldn't really say that there are too many real world examples, but there are some pilot projects that do exist. And then this is going to hopefully change in the coming years. Also, some of the work that Zoltan has done has been quite instrumental in getting this away from just the theory to real life implementation. But in my opinion, we are still far from widespread adoption of these technologies. Okay, another follow-up question, and then we get back to the slides. 1 megawatt of flexibility, how close shall be the buildings for which you are saving energy? Shall they be buildings from one district, or could they be from different parts of the city? Okay, so good question. So if you're talking about energy efficiency or saving energy, then it really doesn't matter where those buildings are, because you're solving a local optimization problem. So it really doesn't matter if one building is in Austin and the other is in Houston, or in different neighborhoods of Austin, I guess. It really starts to matter when you are aggregating that for providing some ancillary service to the grid, or participating in an electricity market. And then it's important that you have all of those assets in the same bidding zone, which is the technical term for it. So for instance, if you are in Belgium, then it doesn't really matter if you're in Brussels or if you're in Leuven, technically. You can simply aggregate those in a virtual manner, and it doesn't really matter how far apart they are, as long as they are in the same bidding zone. This gets a bit more complicated if you have countries with several bidding zones, which is the case for Germany, for Sweden, for Norway, and a few others in Europe. Then you have to really care about, like, if you are still in the same bidding zone, or if there is something that's going on there that is going to change the status. But otherwise, I would say that you don't necessarily care too much about these things as long as you stay in the same region. Okay, good. Then very quickly, we have a demonstration here of what happens if you look at electricity demand at a national level on the left-hand side. versus if you look at it on a building or urban scale on the demand side again. So on a national scale, we see that holidays mean lower electricity demand. On the building side, we do not see the same trends. This, of course, depends on the building, on how it's being used. But if you consider residential buildings, you won't necessarily spot like a huge difference between the time of the year or between the day of the week, or even like it's a lot more stochastic and a lot more dependent on how you're aggregating the demand profiles, which is basically what we're trying to show here. You can also look at how the errors are distributed and how they change over time. So this is basically a depiction of how the grid load errors have evolved over time in Belgium. So we go from 2018 all the way to 2022. And then you can see that something strange happened in 2020. So I guess everyone knows what happened in 2020, when the average forecast error was higher than normal by a considerable margin at both the day-ahead scale and the week-ahead scale, but we did not have that at the most recent scale. So like at a forecast horizon of an hour, things were not too different because COVID did not really affect things at those short time scales to the same extent as they did on a week-ahead time scale. So that's where we really saw the forecast errors increasing quite considerably and dramatically. We also see that on a building scale, the biggest problem is typically observability. So the data quality on the one hand, but also the observability in general, that you simply do not know what is happening inside a building. So even if you are going to have access to the smart meter of a building, you don't necessarily know what is going on inside the building, but you also don't really know what's going on in the neighborhood of the building. So in essence, the building fundamentally transforms into an island that you're trying to well, analyze in isolation, but you have no idea what's going on inside it and what's going on outside of it. So that's another big problem with creating these forecasts, because of course, like if you had information for every single appliance, every single household in a district, you would be able to use hierarchical forecasting algorithms to do a lot better. But what we essentially see is that you only get data from a specific building, and then you have to try to forecast that. And that's usually a small data problem rather than a big data problem. Even when you have that, what this picture or this slide is showing us is analysis of 4 different data sets, 4 different large data sets from 4 different countries, essentially, where you, again, see lots of problems with the data collection. So the black streaks are basically data that is missing. The columns or the horizontal, well, the columns or the vertical axis is basically the timestamps. So this one is probably going from 2009 all the way to 2010. And the rows of this picture are the individual buildings in that particular data set. And then you can see that the quality really varies by the data set, but also even a lot within each given data set. So just for reference, this low carbon London data set contains data for 6,000-ish buildings in London. But then you can see that the quality of data is quite variable even here. The CER smart metering project data collects data from Ireland for 6,000 plus buildings. And again, you see the same problems as well, and the same for others as well. Okay, I will skip this. Well, we don't really have time for how to build forecasters, but I guess we can try to do that in 5 minutes. Okay, if there are any questions, feel free to send them in. Otherwise, we'll try to see how to build a forecaster in 5 minutes. Okay. So there are 3 main components of a forecast model. So basically, you can think about it as y equals f of x, where x is your input data. So that's the left-hand side of this picture. Y is the output, so the thing that you're trying to predict, often load, but often generation or something else in that direction as well. and something in the middle, which we call the model, the forecast model, the predictor, the function approximator. So it has many different names. And this is where you see the deep neural networks and the LSTMs and the LGBMs and all the different types of funky model names that you hear. But keep in mind that that's just one particular part of the picture as a whole. So it doesn't really, well, it doesn't really matter which specific forecast model you choose if you have very bad quality input data or if you don't know what you're trying to predict on the other hand. So if you look at the input data, that's basically typically for predicting load, we have the time of week and the temperature. So those are the Taut models, which are very popular and have been used and abused for several decades now. But in reality, if you want to build these kind of models, you typically build what is known as an ARX model or an autoregressive with exogenous factors. And that basically takes several exogenous factors like the time of the week, the temperature, other weather conditions, but also the autoregressive component, which is essentially the history of the time series itself. So if you're trying to predict the load, then you take a look at the history of the load, but you also look at the other factors that influence the load into the future. So it's important to keep those autoregressive with exogenous factors kind of models in mind. But it also matters how you transform these features. So in many of our use cases, we have seen that if you try to stabilize the variance of the input features, that leads to much better predictions than if you simply use the time series as they are. For load, this is a bit less relevant than for other time series, which are even more non-stationary, but it's still something to keep in mind. Then the output side, you again have quite a few options. Like, for example, do you predict just a single value, or if you predict a whole range around it? As much as you can, I would always recommend trying to see if you can quantify the uncertainty in your predictions, because that definitely leads to an improvement in the quality of downstream decision making. The final component in this is basically the choice of function approximator. So if you're going to go for a linear model, a nonlinear model, what type of optimizer are you going to use in your neural network? Are you going to go for smaller learning rates or larger learning rates? So all of these considerations are really important when you set up your model. But again, keep in mind that just throwing an LSTM or a transformer or some other fancy neural network technology is not going to lead to a better forecast. You really need to think about this problem in a holistic manner. The last thing that really matters is to evaluate these forecast models to see what makes a good forecaster, and their error metrics are important. So you need to take a look at how accurate your model is, but you also need to take a look at the distribution of those errors. So whether they are autocorrelated, whether they are normally distributed, so a lot of other considerations. But you also need to think about the out-of-sample generalization, because for instance, if you have only seen data for the summer and you're going to test your model during the summer, then you cannot really be sure that the model is going to perform well during other times of the year. So something to keep in mind. You also want to make sure that your forecast models are as scalable and computationally efficient as possible, so that you don't really run into problems with having to wait for long times before you can make the prediction or while you're training your model. So again, very important things to keep in mind. Last slide, and a shameless plug to the work that we do in our lab. So we are trying to create a community-driven energy forecasting benchmark. So if any of the stuff that I've talked about in the past few minutes is of interest to you, please feel free to reach out to me or to Attila Balint, who is a PhD student who is working with us on setting up this energy forecasting benchmark, where what we are trying to do is we are trying to crowdsource forecast models. We bring the data, you bring the forecast models, and then we see how those forecast models work with all the data that we can find and scrape from the internet. So with that, I conclude. I think that we are just 1 minute over time, which is still okay. But yeah.
Right on time.
What?
Thank you, Hussain. A round of applause for Hussain virtually and locally. Thank you. Those of you who have to leave, you can leave. If you have, those of you have a question online, you feel free to ask a question for Hussain. Is there a question maybe? There were a lot already answered. Yeah, there's one there, Hussain. Do you want to take that?
Yep, definitely. Okay. I've heard that for the forecasting demand in retail, it's considered to be normal to have 40% error. What error is considered to be normal in energy forecasts? Yeah, so that's an interesting question. You always, so if you go back to the slide that we were looking at earlier, so you can really think about this as a question for like what time scale are you really interested in? So if you're at the top of the that spatial aggregation scale, so if you're only considering a single building or a single household, single commercial building even, then you are definitely going to get mean absolute percentage errors which are in excess of 100% even. If you go to the very bottom of this picture, then you already get something which is probably going to be around 5-6%, probably not more than that. And if you then aggregate it all the way to a country scale, you're probably going to get somewhere. So for European countries, we have seen this to be around 1.5 to 3%, roughly. So that's not a lot of error. The bigger problem there is usually like that you know very well what's going to happen tomorrow. But then there might be small disturbances, like, for example, this thing which is known as the EastEnders effect. I don't know if Texas has something similar, but basically that's the effect where you have like a very popular TV show or something that's happening, and then everyone basically goes to have a cold beer during the advertisement break or something, and then they basically open the fridge, go to the bathroom, basically leads to a lot of electricity consumption that you may want to forecast specifically, but that doesn't really show up in your overall mean absolute percentage errors. So yeah, I don't know if that answers your question, but that's a roundabout way of saying that it really depends on the scale that you're considering.
Cool. Thank you, Hussain. Thanks everybody for attending. I learned a lot, so this was very cool. A nice overview of the markets and how things are connected. Like you said, we have our work laid out for us from the building side and reduce the load as much as we can and provide some demand response services. So let's see what's the future hold. Thank you, Hussain, and we'll see the next webinar in 2 weeks. Next week is spring break.
All right. Thanks a lot for having me, Zoltan, and thanks everyone for the questions and just in general for having me.